In this lecture, I will be reviewing how to balance redox reactions the complete way. Okay, I previously have been teaching a more simplified version of the process I'm going to teach you today, which is balancing a redox reaction in an acidic environment. Okay, so we've been looking at very simple examples of redox reactions that actually follow the rules that I'm working with today that you have not seen if you've been in my class. Okay, very simple, but it deals with reactions that are a little more complex than what we're seeing. So let's begin. So I did a reaction, and I actually have it posted, where we dropped nitric acid on copper, and we've seen that the nitrate ion is a pretty strong oxidizing agent. It can force copper to reduce, whereas the hydrochloric acid cannot. Now this is the reaction written, and it's not balanced, and you can certainly try to balance this the old-fashioned way, but I want to make a point here. The way that I wrote the reaction is not how it would be written in a more advanced class. Okay, most of the time we use something called net ion reactions, and let me show you how this reaction would look, okay, if you took out the spectator ions. So we have copper, no problem here. Now this is a strong acid, nitric acid, as we've talked about. So this is going to break apart into H plus and NO3 minus. Okay, but I'm just going to use NO3 minus right here. I'm just going to do this, okay? And then I'm going to have, well, this is soluble, so this would be copper plus 2, and you would have nitrate ions, okay, that are soluble, and then we would have NO2. So this is how a reaction may be presented to you, let's say in a college or AP class. You may say, Mr. Grotsky, where did the H plus go? Where did the water go? Okay, well, we're just pulling out the actual components that are undergoing the redox reaction, as we've done previously, except before we were pulling out the elements. Okay, and that works when you have metals, but not so much when you have compounds that are acting as, in this case, oxidizing agents. Okay, so this is how it will look to you, and believe it or not, we're going to actually produce the water and the H pluses, okay, and we'll see why these nitrates, okay, are doing what they're doing. So if you look carefully, we have a nitrate staying as a nitrate, so there's some spectator nitrates going on here, and then we have a nitrate going to NO2, and so honestly, we would be presented with just this form. Okay, I wrote the whole thing out, and I'm going to show you how we get back to this result here, and at least make some sense of this reaction. So let's begin. So if I look at my net ion reaction here, all right, I've got copper 0, okay, no questions asked about that. Okay, oxygen is -2, and then my nitrogen, okay, there's what, 3 of these oxygens, that's -6 overall, so this whole thing has to be -1 because it's a polyatomic ion. So the nitrogen, of course, is +5. Okay, we've already talked about assigning oxidation numbers, and I'm just going to get rid of that. All right, so the NO2 quickly, -2 for the oxygen, okay, +4 for the nitrogen. Obviously the copper is +2, and I knew that because each nitrate's -1, but again, this is how it would be given to you in a more advanced form. Okay, so clearly, okay, N plus 5 becomes N plus 1, so in this reaction, you can see N is getting reduced, copper obviously is going up in charge, so it's losing electrons. So let's start with the copper. As we've done already, copper is an element. It goes from copper 0 to copper +2. All right, and when you balance the redox reactions in the more advanced form that I'm showing you in an acidic environment, you start by balancing the chemical first. There's one copper, there's one copper. Okay, second thing is you balance oxygen and hydrogens, and guess what? We don't have any, so we're left with the final thing we balance with is electrons. Okay, so we need 2 electrons on this side to make both sides have the same charge and conserve the charge on both sides. There's a conservation. Now, Mr. Zagrodsky, that was exactly how we've done it already. Yeah, because we didn't have any oxygens or hydrogens to balance. So remember, the first thing we do is we balance the chemical first on both sides. Then we balance oxygens, then we balance the hydrogens from the oxygens, and then the total charge with electrons. So let me show you. Okay, it's going to start to appear right now. We have a nitrate. We're going to pull NO3 out. Now, previously, in more simplified versions, we'd pull the N plus 5 out. Okay, well, the big grown-up method is here. We're going to pull the nitrate because it's essentially we don't have an N plus 5. I mean, we do, but we don't have that chemical. We can't arbitrarily say, hey, get me some N plus 5 at a store. No, you need some nitrates. Nitrates are where the N plus 5 exists, so it's more realistic to write this whole compound. Okay, so we got to balance this first. Well, we know that the nitrates become NO2. Okay, so I'm just writing what it becomes. And once I do that, I balance, okay, everything else. There's one N here, there's one N here. Now, if there was two N's here, and I know it makes NO2, I'd have to put a 2 here. But in this case, because NO3 minus becomes NO2, it's clearly that there's one N per each, and I'm good. But what's not good is the oxygens. Okay, unlike this element where it's just the element, we have an oxygen involved. And there seems to be always an oxygen involved because oxygens love to make oxidizing agents. They love to surround a chemical and draw the electrons in. So in any case, it's very common to have this scenario. So what we do is we balance this extra oxygen by writing a water. Okay, so the first step is you balance your chemical, okay, you're dealing with. It's a 1N to 1N, so we were good. Then we balance the oxygens with water. Now I used one water because one water has one oxygen. So if you look here, one oxygen, two oxygens, three altogether, three on this side. So we're good. But what we just did by balancing the oxygens, we created some hydrogens that didn't exist. So we're going to balance these two H's by writing 2H plus on this side. Since it's in an acidic solution, it's easy to do this, and since it is an aqueous solution, we have the waters. So notice the H pluses are arriving. And of course, the water is taking some shape. So these chemicals are starting to pop up in our redox reaction when we didn't have them initially. Okay, well, we're not done yet. We've balanced everything except our charge. We balanced the O's with the water. We balanced the what? We balanced the extra H's with the protons. Next step is to balance the charge. Well, this side is neutral. This side, okay, +2 and a -1 is +2 overall. So to make both sides have the same charge, I need an electron here. Okay, and we've done that already. We just didn't have these little specifics that we're talking about today. So how do I do this? Well, I'm going to get rid of, well, the next thing I got to do for this to totally balance is I have to balance the charge. This reduction half reaction is taking in one electron. This copper is releasing two. So if that doesn't work, we have to balance these electrons. So what we do is we have to have a common factor. Well, this is simple. This guy produces 2. This is accepting 1. So I'm going to multiply by 2. And when I do so, this gives me 2 electrons, 4 H pluses, 2 nitrates, 2 NO2s, and 2 waters. And again, the reason why I multiplied by 2 is so that I can cancel out my electrons. My charge has been conserved, because if I don't, then I'm saying that electrons are being created or destroyed, and that's not the case. All right, so once I have balanced my electrons, the reaction is balanced. I'm going to write so I'm going to now just combine these two half reactions, and I get 4H plus 2 NO3 minus, okay, can't fit the copper, plus copper, gives me 2 NO2s plus a copper plus 2 plus 2 waters. And this is the correct complete balanced half reaction, between copper and nitric acid. And you see Mr. Grodsky, whoa. Looking up top here, okay, how does this look similar? Well, this top reaction, again, is not written as correctly as it should. This acid is strong, so it's a sham, as I keep saying in class. It's really free, what, protons. This is not together. This is free ions, too. So if you look at that, it kind of makes some sense. Now, notice we have 1 copper, 4 H pluses. So let's put that 4 in there. 2 nitrates. Whoa, that would give me 4 nitrates. That doesn't seem to be jiving with me. I'll get back to that. 2 NO2s. Okay, 2 waters. Okay, 1 copper plus 2. But there's no nitrates here. There's no nitrates in my correct balanced redox reaction. Where'd they go? Well, if you look carefully with me, only 2 nitrates, okay, only 2 nitrates, okay, of the 4 I have listed here actually went under what? Reduction. 2 of these became 2 of these. So if I've got 4 what? Nitric acid molecules, 4 protons were completely used in the redox reaction, no questions asked about that. But 2 of the nitrates underwent reduction, but 2 of them are now free. Okay, now we don't write them on both sides because if you think with me for a second, we have another 2 nitrates that didn't undergo any reduction or oxidation. So we had 4 altogether because you need what? 4 H pluses, and they came from the nitric acid. So you guess what? You have 2 NO3 minuses that are free on this side. And what we do in chemistry, especially in the more advanced form, is we get rid of spectator ions. So that's the overall. Okay? Now, one thing you should do when you're balancing is you should check to make sure the charge on both sides, just to make sure. So when you're done balancing, you should basically check your charge. So if you notice, I have +4 and I have what? -2. So this is a +2 on this side, and they should equal each other. Charge must be conserved here because electrons were conserved. And if you notice, NO2 is neutral, water is a neutral, but you have a copper that's +2, and it checks out. So this is a correctly balanced reaction. Okay, now these two are how they would be given on an AP or freshman level, sophomore level, okay, college level course. And we're going to balance these now using the correct method. Okay, so I'm going to go pretty quick here. You can stop right now and try this on your own, and then you can see me how I would go about doing this. So if you want to stop this now and try number 2 using the full method that I just described, go ahead, stop now, and I will continue. So I'm going to pause for a couple seconds. Okay, so I'm assuming you either want to continue with me reviewing how to do this, or you've done this and see if you get the same answer. So here's what I'm going to do. I'm going to pull out Cr2O7, -2, and it becomes, well, chromium +3. Can't become chlorine, and there's no oxygen, so the chromium, okay, here becomes chromium +3. Now, you may want to know what charge chromium is, but I don't care. I know it's going to chromium +3. Okay, so the first thing I have to do is balance my chromiums. There's 1 chromium here. I'm sorry, there's 2 here. There's 1 here, so I throw a 2 right there. Okay? Now balance the oxygens. 7 over here. Oh, there's none here, so I need 7 waters. Cool, my oxygens are balanced, but now my H's aren't. I have 14 H's on this side. Yep. I'm going to need 14 protons on this side. Okay, everything's balanced except for charge. On this side, I've got a +6 charge. On this side, okay, I've got -4 and 14. That's +12. I have to put the electrons in to balance the charge. Obviously, I'm going to need 6 electrons, and I'm going to put them on this side. Why? Because a -6 and a +12 gives me a +6, and now I have +6 on both sides. My half reaction is now complete. All right, let's do the other half reaction. Okay, we got the chlorine negative going to Cl2. Hey, the first step is balance what we have here. 1 chlorine, 2 chlorines. I need 2 here. There's no oxygens, there's no hydrogens, so there's no waters and protons involved. So I'm just left with balancing the charge. -2 on this side is a 0. I need 2 electrons on this side so that both sides of a half reaction have the same charge. Okay. Now, before we combine, we have to evaluate the electrons and balance them. This top one is absorbing 6. This bottom one is releasing 2. So we have to have the same number of electrons. So to have a common number between 6 and 2, okay, 6 is going to be our answer. So we're going to multiply everything by 3 here, because 3 times 2 gives me 6 electrons. And now my electrons are balanced, and now my reaction is automatically balanced. Add everything together and cancel. There are 6 electrons, okay? There's no anything else I can cancel, so it becomes 14 protons plus your dichromite ion, just one, plus 6 chloride ions, gives you 2 chromium ions, plus 3 chlorines, and 7 waters. And that's the balanced redox reaction, net ion reaction, right? We're separating the ions if they're soluble. Okay, so what I'd like you to do now is do number 3. Okay, I'm going to pause this, and when you click back on here, I'm going to show you my solution. So pause this now, and I will come back to you with everything completed. Okay, so here is the answer that I got, and again, the overall answer is here. Okay, seems a bit complex, but not really. Okay, it's the net ion, taking out spectator ions, and notice water and H pluses appeared that weren't there. Okay, in any case, notice something here. When I did my half reactions, I had to multiply this one by 5 and this one by 2, because when I originally did this, I got 5 electrons for this reduction half reaction, and I got 2. So I needed to have the same number, so I used the common factor of 10 between those two numbers, so I had to multiply and distribute the 5 all the way through. So the red numbers, they represent me multiplying by either 5 or 2 to make sure that I had the same number of electrons being absorbed and released. And then, of course, I canceled my electrons out and gave my overall. Now, in the examples that I showed you here, unfortunately, I didn't give you a good example where you could have protons on both sides. Some of these types of reactions could have protons on both sides. For instance, you may see 16 H pluses, and if, let's pretend that this had, let's say, 8 H pluses on this side. Okay, so you would get rid of these 8, and you would get rid of 8 of these 16, and you'd be left with 8 overall. So just because I'm just balancing out the electrons, the 3 examples I gave you, I didn't show you one where you could be canceling out the extra protons. Or waters. If I had a water on this side, let's say I had, let's say I had 5 waters over here. Well, this would all go out because I'm producing 8, right? And this would go to 3 to cancel both out. So just be aware it's not only just electrons, it could be other elements or other compounds in these reactions, especially the water and the protons, that could be balanced. Okay, now let's move on to Regents Land. For those in New York State, we're not going to have any of this. I'm exposing my honors to this because, or my AP students are reviewing with this. But in Regents Land, okay, we'd be giving these net ion reactions. Now they call it net ion because the spectators are gone. This could be something like aluminum nitrate, okay, or let's do aluminum chloride. This could be aluminum, that's not a good example. Yeah, I'll do aluminum chloride. This could be, I'm sorry, not a good example. This could be copper chloride, pure aluminum, and this could be aluminum chloride. And by the way, for my students, we did this lab. We dropped aluminum and copper chloride, and we produced copper, and we said we made aluminum chloride. But as I keep telling you people, we write it this way, but it's really a sham. If it's soluble, it's really what? It's really copper plus 2 ions and chloride ions. So this would be soluble as well, although aluminum chloride is less soluble. And what we would do is we would get rid of the spectator ions. So if you just get rid of the spectating, and in this reaction, the ion just hanging around would be the chloride ion. So if you get rid of your spectator ions, you'd be left with this overall net ion reaction. We've talked about net ion reactions. So you know that overall net ion reaction in a strong acid, strong base, acid-base reaction is H plus OH minus gives me water. We're taking out what? All the spectators. This could be HCl. This could be NaOH. That breaks apart to H plus, Cl negative, and so forth. The Cl negative and the Na plus do not ionize water, don't do anything. They're just spectating, so we take them out. Okay, so let's get to this. All right, so Regents Land, you have this. Now, some people suggest you write half reactions, and I say that's a good place to start. Copper plus 2, becomes copper 0, okay, plus 2 electrons over here. Aluminum 0, okay, becomes aluminum plus 3 electrons. And just like it did in the more advanced ones, okay, you've got to do what with the electrons? You've got to balance them. So a common factor here would be 6 electrons on both sides. So I times this by 3. That gives me 6. Distribute that. I'm going to times this side by 2 because this gives me 2 times 3, 6 electrons. And now my electrons, okay, are going to balance, and then I add everything together. 2 aluminums plus 3 copper plus 2s gives me 3 coppers plus 2 aluminum plus 3s. And I'm going to put this 2 right in there. I'm going to put this 3 right in there. I'm going to put this 3 coppers right in there. And you guessed, I'm going to put this 2 aluminum plus 3s right in there. And you remembered, we balanced this reaction in that stoichiometry lab as 2, 3, 2, 3. Okay, but we're just looking at the redox part of this reaction. You balance the electrons, you balance the redox reaction always. Okay, now, is there another way to do this? Okay, that we don't have to have right half reactions. Well, I suggest you write the half reactions, but you could look at this another way. Okay, let me show you. Let's get rid of all of this. Okay, and there's a way to do this, but I suggest half reactions is your way of thinking, but some people think of it this way, and I'm just here to help people. So aluminum 0, this is copper 0, this is plus 2 minus 3. Okay, well, I got 1 aluminum, 1 copper, 1 copper. Some people would say on a test, hey, this is balanced. But if you notice something, the total charge on this side is plus 2. The total charge on this side is plus 3. That's not going to work. Charge must be conserved as long as with mass and, of course, energy. So how do I make this side be plus, have this, what would be the common charge between them? Well, if you remember, it was 6 electrons, so we want plus 6 on both sides. So I would take a 2 here, and I would take a 3 here. So we have, again, I'm sorry, we have a 2 here for the aluminum to make this a plus 6. Okay, and then, well, if you have 2 aluminums on this side, you need 2 aluminums here. This side is still plus 2. Notice that doesn't change the charge because aluminum 0, but we still have a plus 2 and we need a plus 6, so we would have to put a 3 here to give me a plus 6, but 3 coppers on one side gives me 3 coppers on another. So that's another way to do this without the half reactions. I know it's blasphemy for me to show you something without half reactions, but that's a skill that some people like to look at. Let's look at the next one. Okay. Oh, plus 2 on what? Plus 2 on this side, plus 2 on this side. 1 magnesium, 2 H's, 2 H's. My friends, in chemistry, we are balanced. Okay, if you do your half reactions, you'll see that. So again, it's a way to save some time. Let's do this one. Okay, zinc and zinc plus 2. So we're doing here, we're plus 6 overall. We're plus 5 overall. Okay, so a little more problems here. So what can we do here? Now, if you run into a scenario you just can't figure it out in an easier way, then half reactions are your friends. Okay, but so in this case, I may say, well, plus 5 and plus 6, I just can't see it. Then do your half reactions. You know, you do your zinc 0. Okay, go to your zinc plus 2. 2 electrons. And you go to your chromium plus 3. Oh, bad Grodsky. You do your chromium plus 6. Always keep them on the same side. Okay, and you go into chromium plus 3. Of course, to do that, you need to have what? 3 electrons being absorbed, because we're still having the same electrons or the same charge in both sides of a half reaction, whether we're doing the more advanced method or the shortcut method here. Okay, and 3 and 2 need a common factor, 6 electrons. So we would go 3 times 2 is 6. Okay, this would be 2. 2 times 3 is 6, and 2 here. And electrons cancel, and we'd have 3 zinc, 2 of these, zinc with 3, chromium plus 3 is, if you see up here, 2. Okay, and if you check, very simply, 2 two chromiums, this is plus 12 altogether, and we need to have plus 12 on this side, so 2 times 3 is plus 6, 3 times 2 is plus 6, and we have the same mass and same charge in both sides is plus 6. Okay, I'll quickly finish this out. Alright, you try 7 and 8, and I'm just going to give you my answers in a second, so I'm going to pause this now, and you do 7 and 8, and I'll show you the answers. Okay, so here are my answers. Number 7 was already balanced, right? Plus 3 on this side, plus 3 on this side. 1 silver, 1 iron, 1 iron. Now, if you did the half reactions because you weren't sure by doing that quick, easy method here that I was showing you, you'll see that you absorb 1 electron, you release 1 electron, electrons cancel, and nothing in front implies 1 for everything. So that was already balanced. Okay, the next one, I did half reactions just to show, but some people could have figured it out just to put the 2 on both of these sides, right? If you need put a 2 here, it's plus 6, plus 2 is plus 8. How to make this side plus 8? Put a 2 here. Okay, but if you do the half reactions, this gives off 2 electrons. Sn plus 2 is going up in charge because it loses 2 electrons, and Fe plus 2 is getting reduced. It's going down in charge by actually losing or absorbing 1 electron. I times by 2 and distribute that here to make sure the electrons are balanced. The common factor is 2. And I plug them in. Either way, it's a pretty fast method, and these are the Regents level, New York State Regents level way to balance half reactions, net ion reactions. Okay, and of course, I reviewed how we do it in the real world, how you really balance redox reactions in an acidic environment. There's also a basic environment, but I did not cover that in this lecture.